These two graphs give us a visual representation of two very important theorems that we're about to introduce. So keep in mind what we did was took a function that originally had no absolute maximum or minimum because our function continued increasing to infinity, decreasing to negative infinity. Then we restricted the domain to some closed interval, and then we can identify both an absolute maximum and absolute minimum. So whenever we're dealing with functions on closed intervals, so if we have a continuous function whose domain or values are for x are restricted to some closed interval from a to b, then we're guaranteed to have both an absolute maximum and an absolute minimum on that interval. So if our function has a restricted domain on that closed interval and it's continuous, we're guaranteed to have both. Another theorem, which helps us locate where those extrema will occur, tells us that if absolute extrema occur, then they must occur at either critical values or at the endpoints for that closed interval. So essentially what we're going to do is find any critical values for the first derivative, identify our endpoints, which will be given to us, and then evaluate the function at all of those values. Or to break that down into a little bit more of a step-by-step method, first thing we'll do is verify that our function is continuous on that closed interval from a to b. We'll find all critical values, which again come back to the idea of where our derivative function is either equal to 0 or our derivative is undefined. We'll evaluate f at the endpoints of that closed interval that we're given and all critical values. So since the absolute extrema must exist at the critical value or endpoints, we'll compare those different function values and identify the absolute maximum as the largest function value that we get, and the absolute minimum as the smallest function value that we get. So we just need to identify the endpoints which are given to us, any critical values, plug all of those back into the original function, and then just rank those different results. So in our first example, we want to identify any absolute extrema for this function on the closed interval from 0 to 5. We're dealing with a polynomial function, so it's always continuous. So we can find the derivative of this function to be 2x minus 6. Setting that equal to 0 will give us a critical value at x equals positive 3. So we have a critical value to consider and our two endpoints. So we can evaluate our function at f of 0, that first endpoint, which would give us 0 minus 7, or negative 7 as a result. We can evaluate the original function at the critical value, which in this case we only have one to consider, which is 3. So this would give us 9 minus 18 minus 7 is going to give us negative 16 as a result. And then we have the other endpoint to consider, f of 5, which would give us 25 minus 30 minus 7, or negative 12. So in this case we only had one critical value, so only 3 different points to consider. If we had more critical values, we'd have some more evaluating to do. What we can see is that negative 7 in this case is our largest function value. Negative 16 is the smallest function value. So in this case, our function f of x has an absolute maximum at f of 0, and that function value specifically is going to be negative 7, and it has an absolute minimum at f of 3, and specifically that function value will be negative 16. So once we get those 3 values, possibly more if we have more critical values to consider. We evaluate the original function and compare those results to identify the largest value as our absolute max, the smallest value as our absolute minimum.